Alright, so we are starting chapter 7 here. I need you to turn to page 156. Page 156. So today we're looking at shapes of different covalent molecules. As you probably are still thinking about what you have done in chapter 6, we look at covalent molecules itself, and we're talking about how different atoms within the molecule share electrons, eventually allowing them to fulfill the octet rule. That is the ultimate goal of each atom that is bonded together through the covalent bonding. Alright, so on page number 156, we are discussing the valence shell electron pair theory, valence shell electron pair repulsion theory, VSEPR. So it says here the valence shell electron pair repulsion theory proposes that the shape of a molecule is determined by the outer valence electrons. As electrons are negative, the pair of electrons repel each other, giving molecules their shapes. Alright, the point here, if you still remember previously, we look at a particular example, which is methane, and we know methane has a chemical formula of CH4, and carbon is in group 14. It has 4 valence electrons. It wants to share 1 electron or 1 valence electron with each hydrogen, ultimately allowing it to have 8 valence electrons. And for methane, it has a shape, a tetrahedral shape. And how it gets its tetrahedral shape has a lot to do with this particular theory. So what this theory is suggesting, that the valence electrons are repelling against one another because they are of similar charge. And because of the repulsion, it will ultimately allow that particular molecule to have a particular shape. So we are looking at different shapes for today. So I'm going to move on to the next slide. Alright, so this is here the electron pair repulsion, page 156. In general, atoms in covalent molecules are the most stable when they have 8 electrons in the valence shell. It is known as the octet rule. It says these 8 electrons arranged into 4 pairs of electrons. So this is the example that we have discussed in chapter 6 itself. As you can see at the bottom diagram that we have here, this is the structure of methane CH4. And this is an electron dot diagram. We did discuss this previously as well. Electron dot diagram is also known as the Lewis diagram. It is not the same as the valence shell diagram. They are two totally different diagrams. All right. When you're talking about valence shell diagram, you're talking about how the electrons that is being shared, you use a line instead to show the electrons that have been bonded. In this case, you're using dots and crosses. All right, so there is a difference between electron dot and valence structure or valence diagram. All right, so it says here, for example, I'm reading the second paragraph. It says here, for example, the carbon atom in methane is covalently bonded to 4 hydrogen atoms. In this arrangement, the carbon atom shares a pair of electrons. One pair means that you have a total of 2 electrons that we share, one from each atom. Alright, that's what it means. It says here the 4 pair of electrons give the carbon atom a stable octet. In this diagram, the dots represent electrons donated to the single covalent bond by the carbon atom. The crosses represents electrons donated to the single covalent bond by the hydrogen atoms. Alright, so the next slide will show you that particular shape, and the shape that we have discussed for methane is tetrahedral, and I'll explain more why it is tetrahedral. I'm going to move on to the next slide. Alright, so based on what I've mentioned about the methane molecule, as you can see here, methane is CH4. The electron pairs in single covalent bonds repel each other. It says the repulsion forces, so I'm reading this diagram here. It says the repulsion forces the bond as far apart as possible, arranging the hydrogen atoms into tetrahedral shape and angle 109.5. So the angle between the hydrogen atoms in this methane molecule is 109.5. Alright, so how this works is that the valence shell electron pair repulsion theory, VSEPR theory, says that all of the valence electrons want to repel each other because they are of the same charge. So think about this, of the valence electron on the hydrogen atoms and valence on the carbon atoms want to repel one another, and because of that, it wants to ensure the electron as far apart as possible, and the angle that we have is 109.5 as a result. Because usually you would expect it to be probably like 90 degree, but in this case it's not the case because it wants to be as far apart as possible, and the angle that it comes out with is 109.5. All right, and that is the reason why the methane structure that you have it does have a bond angle of 109.5. All right, I'm just going to move on to the next slide. All right, lone pairs of electrons. It says not all electron pairs in molecules exist as covalent bonds. Some electrons form a non-bonding pair of electrons known as lone pair of electrons. So what are lone pairs of electrons? Lone pair electrons are electrons that are not being bonded. So we will go through a few examples to see what lone pair electrons are. Basically, if the valence electrons are not being bonded in any way, they are known as the lone pairs of electrons. So it says here, in the VSEPR theory, lone pairs of electrons are treated in the same way as electron pairs in covalent bond in order to determine the shape of molecule. I'm just going to move on to the next slide. Alright, so this is an example for ammonia. It says that in the ammonia molecule shown below, the nitrogen atom has a stable octet made up of one lone pair of electrons and 3 single bonds. The 4 electron pairs repel each other to form a tetrahedral arrangement. So technically saying, you should be able to get the tetrahedral shape. But the issue that you have here as compared to methane that we had previously is that you can see the diagram at the bottom. You have something called the lone pair. Alright, as you can see, I'm circling this for you. The lone pair of electron. So 3 electrons from nitrogen is been bonded to hydrogen, 1 to each hydrogen, but it's left with 2 lone electrons. That's the reason why you have that lone pair electrons. The lone pair electron is still repelling. That's something that you must be very clear. According to valence electron pair repulsion theory, any valence electron wants to repel one another because they are of the similar charge. So as you can see here, ammonia, even though it's trying to achieve that tetrahedral shape, but because it has the lone pair electron on the surface of nitrogen, eventually you get what we got here, which is known as pyramidal shape. And what this is trying to say here, and I highlight the top part, and this is very important, it says the lone pair occupies slightly more space than the bonding electrons so that the 3 single covalent bonds are pushed closer together. So what this is saying that the repulsion from the lone pair electrons is slightly larger in this sense because it occupies more space than electrons that have been bonded, and that's the reason why the bond angle that you have between the hydrogens at the bottom, is less than 109.5. Why is it less than 109.5 degree? It's because of that lone pair occupying more space than the bonding electron. So you have to be very clear on that. So technically saying, you should be getting the tetrahedral shape, but because it has the lone pair electron on that surface of nitrogen, eventually what you get is a pyramidal shape, and the bond angle between the hydrogen atoms is slightly less than 109.5. Alright, I'm just going to move on to the next slide. So this is for water molecules. For water molecule H2O, if you do your calculation, oxygen is in group 16, yes. 6 valence electron, it just needs 2 more electrons for it to become stable. Hydrogen has 1 electron each, it needs 1 more electron for each hydrogen for it to become stable, to fulfill the octet rule. Alright, the point here is that when you're talking about water molecule, it has 2 lone pair electrons, 2 lone pair electrons. So how this works here, so how these 2 lone pair electrons, is that these electrons, the lone pair electrons and the electrons that have been bonded, they do repel one another, they do repel each other, it forms a tetrahedral arrangement. But because it has 2 lone pair electrons, what you get here, you get a V shape or the band shape as stated here, and eventually the bond angle that you have between the hydrogen is less than 109.5 as well. And you could also predict saying that the bond angle between the hydrogen here will be even lesser as compared to the bond angles of hydrogen in ammonia? Because in ammonia it has 1 lone pair electrons, and in water molecule it has 2 lone pair electrons. So the repulsion that you have here will be even greater between the lone pair electrons because they are taking even more space, and eventually the bond angle between hydrogen will be 109.5. So you have to be very clear with the shape that you have. If you're talking about ammonia, it has the pyramidal shape. In water you have the V shape. Why do you have these different shapes? Even though technically saying they are tetrahedral in nature, is because of the presence of these lone pair electrons. So lone pair electrons, once again, are the electrons that are not bonded in any way. They are the valence electrons that are not bonded in any way. Then they are occupying more space than electrons that have been bonded, which is the reason why ammonia has a pyramidal shape. Its bond angle between hydrogen is less than 109.5. For water molecule, it has 2 lone pair electrons. Its bond angle is also lesser than 109.5, and it has a V shape. All right. So I'm just going to move on to the next slide. So this is for hydrogen fluoride. Hydrogen fluoride, as you probably can see here, it has 3 lone pair electrons. So we start off with ammonia. We say ammonia has 1 lone pair electrons. Water molecule has 2 lone pair electrons. Hydrogen fluoride here will have 3 lone pair electrons. So it says here the fluorine atom has a stable octet makeup of 3 lone pairs and 1 single bond. The 4 electron pairs repel each other to form tetrahedral arrangement. Therefore, the hydrogen and fluorine atoms form a linear molecule. So linear means that bond angle, as you could probably predict, is 180 degrees. Why is it so? Because these 3 lone pair electrons, yes, they have a larger repulsion as compared to electrons that have been bonded, but the point here is that these 3 lone pair electrons repel at the same rate, and they are taking up of the similar space, and eventually you will have this particular linear molecule. So this is these 4 lone pair electrons, or these 3 lone pair electrons, and that 1 bonded electrons, they form the tetrahedral arrangement due to mutual repulsion, and as a result it will have the linear molecule. Alright, so you have to be very clear with the shape, and you have to be very clear with the bond angle. If it has 1 lone pair electron, as you can see in ammonia, you get pyramidal shape, bond angle less than 109.5. Water molecule, 2 lone pair electrons, it has an even greater repulsion in that it will get a V shape. Its bond angle is also lesser than 109.5, and in hydrogen fluoride, as you can see, the bond angle between hydrogen and fluorine will be 180 degrees because of the repulsion from this lone pair electron, and in this case you have 3 lone pair electrons, so you get a linear molecule. Alright, I'm just going to move on to the next slide. Alright, predicting the shape of molecule. See, predict the shape of molecule of phosphine, pH3. So if you have a structure of pH3, chemical formula of pH3, we know that phosphorus is in group 15, it has 5 valence electrons. So you can see there is a structure here. Eventually, for phosphorus will have 8 valence electrons, which means that it will fulfill the octet rule. Hydrogen will have 1 extra electron, which means to have 2 valence electrons at the end of this particular bonding, and this is in a tetrahedral arrangement. It is arranged as pyramidal. Why is it pyramidal? It's because it has that 1 lone pair electrons, which means that that particular pair electrons is not bonded in any way. As you can see at the top, I'll highlight this for you at the top. And this is the reason, even though it's pyramidal, even though it's tetrahedral, it is being arranged in the pyramidal shape because of that 1 lone pair electron. So you can also predict in this case that the bond angle between the hydrogen is less than 109.5. Alright, so there's a question here at the bottom. I need to try it yourself before we discuss it. This is the shape of molecule hydrogen sulfide. So you could probably predict sulfur here is in group 16. It has 6 valence electrons. Hydrogen is in group 1. It has 1 valence electron. So you can predict that in this case, sulfur will have 1 bond with each hydrogen. So 1 electron is bonded to 1 hydrogen, 1 electron bonded to another hydrogen. And probably you have 2 lone pair electrons. Alright, so you can try and predict the shape of the molecule. I'll give you time and then we discuss when we are going to the online session. You can so predict if the structure is, in this case, is tetrahedral in nature, but it has 2 lone pair electrons, so what shape do you get? And will the bond angle be 109.5 or lesser than 109.5? So think about it. Alright, and then we'll discuss it when we go online. I'm just going to move on to the next slide. Alright, double bonds, triple bonds, and valence shell electron pair repulsion theory. So we talk about VSEPR. Once we are still on VSEPR theory. This is a methanol is CH2O. Alright, so it says here a double bond contains 2 pairs of electrons. A triple bond contains 3 pairs of electrons. The VSEPR theory treats double and triple bonds in the same way it treats single bonds and lone pair electrons. So it says, for example, if a central atom has 2 single bonds and 1 double bond, then the 3 sets of bonds will repel each other to get maximum separation. This results in a molecular shape known as triangular planar because the atoms form a triangle in one plane. An example of this structure is methanol. So the point here, methanol has single bond, has double bond. You have to be very clear. A single bond will represent 1 electron is being shared from each atom. A double bond represents 2 electrons is being shared from each atom. So carbon is in group 14. It has 4 valence electrons. Of course, it will need 4 more electrons for it to become stable. So as you can see, hydrogen has 1 valence electron each. So eventually, carbon will have 8 valence electrons. Oxygen here will also have 8 valence electrons because it just needs 2 more. It's in group 16. Alright, the point here is because of the way this particular structure works, you can see eventually it will have a bond angle of 120 degree, because technically saying the lone pair electrons are on oxygen, and for carbon it has that 3 bonds, 2 single bond and 1 double bond, and the angle between hydrogen and hydrogen will be 120, hydrogen and oxygen will be 120, and so on. So it has a shape of trigonal panel. Alright, I'm going to move on to the next slide. This is for carbon dioxide. Carbon dioxide, CO2. So what you will normally need to do when you come across this question, you need to know which group they are in. How do you know? You look at the periodic table, and you can also predict based on the number of electrons that are present, and then you can calculate the number of valence electrons that are present. Alright, so carbon is in group 14, oxygen is in group 16. Carbon here will need 4 more valence electrons for it to become stable. Oxygen will need, or each oxygen atom will need 2 more valence electrons for it to become stable. Alright, in this case, each carbon and oxygen will have that double bond because each of them will share 2 electrons with another atom, because you must remember carbon needs 4 more electrons. So it has a double bond with an oxygen, it has another double bond with another oxygen, eventually it will have 8 valence electrons. And because the repulsion on both sides is technically the same, each side has 2 lone pair electrons. As you can see here, the left side will have 2 lone pair electrons and the right side will have 2 lone pair electrons. It will have a bond angle of 180 degrees. So this will be a linear molecule and it will have a bond angle of 180 degrees. I'm just going to move on to the next slide. Alright, C is for hydrogen cyanide. Hydrogen cyanide. Hydrogen cyanide has a chemical formula of HCN. It has a single bond, it has a triple bond. Single bond means that 1 electron is being shared from each atom, and triple bond means that 3 electrons will be shared from each atom. As you can see here, is a little bit of a tricky situation because hydrogen needs 1 more valence electron for it to become stable. Carbon needs 4 more. Hydrogen, which is in group 15, it needs 3 more. So how this works is that nitrogen and carbon will have a triple bond because nitrogen wants to have 3 more electrons. If you do your calculation here, nitrogen initially have 5 plus 3, it will have 8. Carbon share 3 electrons with nitrogen, so we have 3 more from nitrogen and 1 more from hydrogen. And carbon is in group 14, so it needs 4 more valence electrons. And that is the reason why hydrogen cyanide is a linear shape. It's a linear shape because of the way the repulsion works here you have one hydrogen, you have one nitrogen, you have the carbon that's bonded to hydrogen and nitrogen, and eventually it will have a shape of a linear, and it has a degree of 180. So the bond angle here between hydrogen, carbon, and nitrogen will be 180 degree. I'm just going to move on to the next slide. Molecules that do not obey the octet rule. Alright, the point you have to be very clear is that as much as the atoms within a molecule wants to fulfill the octet rule, sometimes it cannot obey it completely. So there are some of these examples that you have to be very clear. The first example that we have is Borane. Borane is BeHz, as you can see here. Alright, and what you can see from the diagram is that Borane, is consists of boron and hydrogen atoms. Boron is in group 13. It has 3 valence electrons, so it shares 1 electron with each hydrogen. Alright, hydrogen fulfills the octet rule. It just needs 2 valence electrons for it to become stable. In this case, as you can see, boron only needs 6 valence electrons for it to become stable. It's in a little bit of a tricky situation because usually an atom needs 8 electrons for it to become stable, but boron here just needs 3 more electrons. 3 plus 3, so it just needs 6 valence electrons for it to become stable instead of 8. So it doesn't have any lone pair electron, and because of that, this is a trigonal panel. If you still recall, when we are talking about ammonia previously, NH3, we know that ammonia has 1 lone pair electrons. It will have that pyramidal shape. It's not the case with Borane, because Borane does not have any lone pair electrons, even it have that 3 pairs of bonded electrons. That's why it has this trigonal panel shape. I'm just going to move on to the next slide. Alright, boron trichloride, BCl3. Boron is in group 13 once again, and chlorine is in group 17. We know that boron in this case wants to fulfill the octet rule. Chlorine wants to fulfill the octet rule as well. Chlorine, of course, just need 1 more valence electron for it to become stable. But what you need to be very clear here, boron is an exception. It doesn't really need to have the 8 electrons in the valence shell for it to become stable. In this case, boron trichloride, as you can see here, it is stable by sharing just 1 electron with each of these chlorine. So eventually we just need 6 valence electrons for it to be stable, and it has a shape of trigonal panel once again because it does not have any lone pair electrons. Even if it have that 3 bonded electrons, there is no lone pair electrons, and the bond angle between the chlorine and another chlorine is 120 degree. Alright, I'm just going to move on to the next slide. So the next example that we have that does not fulfill or does not obey the octet rule is beryllium hydride. Beryllium hydride is BeH2. As you can see here, the central beryllium atom forms single bonds with 2 hydrogen atoms but has no lone pair electrons. So beryllium is in group 2, and you know that it has 2 valence electrons. In this case, it just needs 2 more electrons for it to become stable, and it does not have any lone pair electrons. That's the reason why it is linear shape. If you think about what we have done previously, when we are talking about water molecule H2O, we know water molecule has 2 lone pair electrons. You get a V or band shape, but in this case, that is not the case. You have just that linear shape, a linear molecule, and you can see that the repulsion here on both sides is the same, and that's the reason why you get that linear molecule. Alright, I'm just going to move on to the next slide. Alright, this is the last example that we have for molecules that do not obey the octet rule. It's a sulfur hexa for SF6. You have 1 sulfur, you have 6 fluorine atoms, and it's made up of central atoms of sulfur with 6 valence electrons. This sulfur atom bonds to 6 fluorine atoms. If you do your calculation here, sulfur is in group 16 and 6 valence electron. Technically saying, for it to fulfill octet rule, it just need 2 more. But in this case, that's not the case. You have a structure which is SF6. Each sulfur will have share 1 valence electron with each fluorine atoms. And because of that, it will have more than 8 valence electrons in outer shell. So 6 plus 6, you get 12 valence electrons in outer shell at the end, and the bond angle between the fluorine atoms is 90 degrees, and the maximum angle possible for 6 electron pair. So the angle here is not 109.5, it's not 120, it's not 180, it's 90 degrees because of the presence of that 6 fluorine atoms. And for them to repel against one another, the maximum repulsion that you can have possibly here is that 90 degrees between each fluorine atoms. Alright, so these are the examples that we have for those molecules that do not obey the octet rule, but you can see that there are not too many of them. Most of the molecules do fulfill the octet rule because they do want to have a maximum of 8 valence electrons in outer shell. Of course, you do have an exception to that. Hydrogen and helium, usually they just need 2 valence electrons for them, or they need 2 valence electrons for them to be stable. Alright. So you do need to complete the questions on the textbook, and then when we meet online, we'll have more discussion on these. And the next few lessons, we will investigate more about the different bonding that can be present other than the covalent bond that we have discussed, and we will investigate on how that can affect the properties of that covalent molecule. Right. Thank you very much.